Hello, nice to meet you. I'm Uchan Yu, a professor of Bugyang National University. My presentation will be optical performance testing, traceability, and maybe reliability testing. I will disappear and there will be my presentation. See you. Nice to meet you again. And I'm happy to join Myanmar LED ODA project. This is my first presentation. The subject is photometry. This is the outline of my talk. I reviewed the IEC standard you sent us, so I derived several categories. Most of my talk will be concentrated on the optical performance, that is photometry. Therefore, I will present optical parameters of photometry, electrical parameters, and reliability, that is luminous flux maintenance, will be shown later. You send us LED lighting standard you want to implement in Myanmar. I'll review the list and categorize like this. So I categorize the LED package lightings and luminaires, control gear, dimmer, interface, LED lamps, and so on, and reliability testing. At this time, I'll present you optical performance testing. Afterwards, I'll present electric performance reliability testing. Luminous flux maintenance will be the main issue. And afterwards, I want to represent optical, electrical, reliability, and IP rating, and so on. Stability will be also represented, I hope. This slide shows you SI units. As you know, there are 7 base units: length, mass, time, current, temperature, mole, and light intensity. For LED lightings, meter and candela are most important parameters. Also, second ampere Kelvin will be used, and other derived units such as lumen, lux, steradian, candela per meter square, watt, and voltage will be also used. In the photometry, optical performance parameters are like this: luminous intensity, luminous flux, luminance, illuminance, color temperature, correlated color temperature, color rendering index, color coordinates, wavelengths, far-field beam distribution, and luminous efficacy. Luminous intensity uses candela as a unit. Luminous flux uses lumen. Luminance uses candela per meter square. Illuminance uses lux. Color temperature Kelvin. Color rendering index, that is CRI, has not unit. Also, color coordinate has not unit. Wavelength meter and luminous efficacy use lumen per watts. And then what is the parameters meaning? Luminous intensity is defined as wavelengths weighted power emitted by a light source in a particular direction per unit solid angle. So they can be expressed as lumen per steradian. Luminous flux or total luminous flux is the perceived power of light by human eye. So human eye is very important and complicated perception. Luminance is luminous intensity per unit area of light traveling in a given direction. Illuminance is the total luminous flux incident on a surface per unit area. Therefore, lumen per meter square. Color temperature means temperature of an ideal blackbody radiator comparable to that of the light source. Color rendering index is ability to reveal the colors of various objects faithfully in comparison with the natural light source. Color coordinates are calculated value from relative distribution spectrum of light. You know wavelengths. So I skip. And luminous efficacy means ratio of total luminous flux to input electrical power. Human eye is important for photometry. In physics, we measure radiometry. So we should distinguish radiometry and photometry. Radiometry is measuring radiation of light in electromagnetic spectrum, but photometry is measuring visible light through the human eye. So photometry is weighted with a certain function to the radiometry. So the conversion of radiometry to the photometry or photometry to radiometry is very complicated. So we compare the parameters of radiometry and photometry. In photometry, we use luminous flux, luminous intensity, luminance, luminous view angle, luminous energy, illuminance. To the contrary, in radiometry, we use radiant flux, radiant intensity, radiant view angle, radiant energy, irradiance. As you know, radiant flux uses watt, but luminous flux uses lumen. Radiant intensity use watt per steradian, and luminous intensity use lumen per steradian, that is candela. Radiance use watt per steradian per meter square, but luminance use candela per meter square. Irradiance use watt per meter square, illuminance use lux, that is lumen per meter square. So we should remember luminous flux, luminous intensity, luminance, and illuminance. I think those are very important parameters for LED lightings. This is a straightforward comparison of photometry and radiometry. In the radiometry, 1 watt is 1, but in the photometry, we use so many values according to the wavelengths. Important point is the wavelength of 555 nanometer. There is 683 lumen. The wavelength of 450 nanometer, 1 watt is 25.9 lumen. And at the wavelength of 700 nanometer, 1 watt is 2.78 lumen. So the radiometry is converted to the photometry to the various values according to the wavelengths. It is very complicated and very important point. Irradiance, 1 watt per centimeter square is 6.83 multiplied by 10 to the power 5 lux at the wavelength of 555 nanometer. Intensity, 1 watt per steradian means 683 candela at the wavelength of 555 nanometer. Also, radiance, 1 watt per centimeter square per steradian means 683 candela per centimeter square at the wavelength of 555 nanometer. The wavelength 555 nanometer is very important in the photometry. To measure LED lightings, optical parameters of photometry very important. So I will review the parameters of the photometry. The most important parameter is luminous intensity in the unit of candela. As I explained, luminous intensity means wavelength weighted power emitted by a light source in a particular direction per unit solid angle. So candela is lumen per steradian. And the radiant intensity of a light source emitting monochromatic light with a wavelength of 555 nanometer releases to 1 over 683 watt per steradian in a given direction. That means the intensity of light in the direction. So that is luminous intensity. So in the case of photometry, The wavelength 555 nanometer and the value of 683 was very important. As I explained, radiant intensity 1 watt per square radian means 683 candela at the wavelength of 555 nanometer. Therefore, luminous intensity of 1 lumen per square radian means 1.464 multiplied by 10 to the power minus 3 watts per radian at the 555 nanometer. So I can summarize like this. If there is one candela isotropic light source is located in the isotropic medium, then the total luminous flux reaches to 4 pi lumen. That is important thing. That's the straightforward relation of candela and lumen. As I explained in the previous slides, photometry is the perception of light by human eyes. So this graph shows you the weighting function of human eye, that is visibility curve. It is peaked at 555 nanometer. So human eyes are very sensitive to the wavelengths of 555 nanometer. To calculate luminous intensity, we use this kind of formula. We measure spectral irradiance by using a spectroradiometer, and we know V lambda from the CIE standard. So multiplying those curves and integrating them by wavelengths, and then we multiply Km, that is 683 lumen per watt. Then we drive illuminance. But we want to calculate luminous intensity. So we should convert illuminance to the luminous intensity. The conversion process is verified by the formulas. This is the previous formula. We calculate illuminance, that is lux. Km has lumen per watt. E lambda, spectral irradiance, use watt per meter square per nanometer. Because V lambda has relative values, so it has no unit. Integrating by lambda, so nanometer. Then we can summarize lumen per meter square. That is lux, right? By using this formula, we can convert illuminance to the luminous intensity. We measure illuminance at the distance of d. I will show you later slide. Lumen per meter square, and the aperture is 100 millimeter square per 0.01 square radian. There is the measurement standard of luminous intensity. So luminous intensity is candela, and then you can calculate, and then you can drive lumen per square radian. Therefore, candela is lumen per square radian. Therefore, I will introduce you measurement of luminous intensity of LED package as shown in CIE 127. They give this kind of formula. Luminous intensity is illuminance multiplied by distance square. D is the distance from the end of the LED to the circular aperture in front of the photometer. Photometer measures illuminance. The numerical aperture is a circular aperture, and the area is 100 millimeter square. Then the distance will give you a solid angle like this. In the CIE standard, there are two conditions of measurement. Condition A is the distance D is 316 millimeter, and condition B, the D is 100 millimeter. In the case of condition B, the unit solid angle steradian will be 0.01 steradian, and the longest distance 316 millimeter, the solid angle will be 0.001 steradian. You can understand the previous calculation I did. You can measure spectrum by using spectroradiometry. That means measuring spectral irradiance. Spectrum will be tested by a grating and CCD array detector in the measurement equipment. This will be explained later. You can summarize the measurement process using a spectroradiometer like this in here, and then you test 2 times. At first, you measure standard LED and calculate the C lambda, and then you measure LED on the test, extracting E lambda, then calculate the calibration factor F lambda according to the wavelengths. It is important that there is a calibration factor according to the wavelengths. And then I will explain total luminous flux, which is unit of lumen. Luminous flux of all direction, that is 4 pi from a light source. As explained, lumen is candela steradian. Radiant flux watt, that is radiant power, is energy per unit time of light emitted, transmitted, and incident in the form of radiation. As repeated so many times, 1 watt at 555 nanometer is 683 lumens. That is important for the photometry. To measure total luminous flux, you use this kind of sphere, that is integrating sphere. By putting the LED or light source in the center of the integrating sphere, if you turn on the LED, the light from the LED will in charge inside all of the sphere. And then if you put a hole one side of the sphere, then you measure the total luminous flux inside of the sphere. In measuring LEDs, you use test LED and standard LED. So you should compare the two light sources. In the case of one-sided LED, such as SMD type LED package, then you can put the test LED and standard LED at the side of the integrating sphere. The subtraction of test LED with standard LED is the same as in the previous integrating sphere or testing luminous intensity. This slide shows you illuminance, unit of lux. Illuminance is luminous flux per unit area, therefore lux is lumen per meter square. Illuminance means the amount of luminous flux projected onto the subject surface in unit area. Let's extract illuminance from luminous intensity. There is a luminous intensity standard of 1 candela. If you draw a circular surface 1 meter square at 1 meter from the center of the standard light source, then the circular area will consist cone angle like this, and then this kind of cone angle is 1 steradian. Therefore, 1 candela per steradian means 1 lumen, right? And then in the area, there is a 1 lumen per 1 meter square. Therefore, it will be 1 lumen per meter square, and it will be 1 lux. So, you derive illuminance from the luminous intensity of 1 candela. Illuminance will be changed by the distance, because illuminance means total luminous flux over area. If there is a light source and then you measure illuminance at the distance 1, d1, then if you measure at the distance of 2, d1, twice of D1, then the illuminance will be decreased by 1 over 2 square. If you measure illuminance at the distance of 3 times of D1, then you will get the illuminance decreased by 1 over 9. That is 3 square. So if you go far from the light source, then illuminance will decrease by scale of distance.